I am doing the experimental report for our group. Next slide, please. So the purpose of the Clapeyron experiment is pretty much just to say that a value that can't be directly measured, such as enthalpy, can be measured through stuff like saturation pressures and temperatures. Next slide, please. This is a bit of the mathematical theory behind it. I'm not going to go over this too much. What's important is the next slide, where you actually make the assumption that changes it to the form right here, which is what we're going to be using to gather our experimental data and determine enthalpy as a function of temperature. Next slide, please. This is a little bit, this is the experimental apparatus right here. You can see that we have a vacuum line right here. We have a pressure gauge with a bleed valve, and then we also have a beaker right here that we are going to be boiling water in with that hot plate. And to the right, you can see that laptop used for data acquisition. All right, next slide, please. Here's a bit about the procedure. Pretty much just says that we turned on the vacuum pump and lowered the beaker to the lowest achievable pressure. After that, we brought the water to a boil, and then data collection started, slowly increasing pressure until we reached just under atmospheric pressure, at which point we opened the bleed valve to prevent any pressure buildup. And then after that, we ceased data collection and the hot plate was turned off. Next page, please. So if you plot the saturation pressure and temperature that you get, you can see that it actually matches the tabulated values very well with a max error of about half a PSI. Next slide, please. And so actually taking this and making it like to where we're actually calculating the enthalpy, which is what we wanted, we need to rearrange all this data in this form here. What's really important is this function right here, which determines enthalpy as a function of temperature, for which in this procedure we're calculating the local derivative as pretty much delta P over delta T for the points right next to it. And so if you go to the next slide, this is the result you get. It's really bad. It's very bad at predicting it, as you can see. If you look at the percent error there on the right, the percent error is really bad, and so we don't like this because there's a lot of noise. And so we fix this by actually, if you go to the next slide, we fix this by applying a piecewise cubic spline fit of this form right here to our temperature, and then you can differentiate it, which gives us a new dP over dt. That's supposed to be a capital T for temperature, not lowercase t for time. And if you go to the next slide, you'll see what you get from that. So it's still pretty bad. You can see actually that near 60 to 90 degrees Celsius, our error actually increases. And this is still a really, really bad model at actually accurately predicting our enthalpy. So what we do is, next slide please, we assume that the enthalpy is a function of the form A plus B times T, for which T is the temperature. If you substitute this in back to the Clapeyron equation, you get this equation right here. And then if you integrate it with respect to T, you get this. And then if you reassign it with coefficients to where it's equal to, like, where it's this form right here, you can then calculate your coefficients for A and B. And so if you go to the next slide, this is what you get. Now, if you look at it, something looks a little weird, right? So this is saying that enthalpy is actually rising as temperature increases, which is actually the exact opposite of what happens in the real world. It actually kind of looks like, if you look at this 2200 kilojoules per kilogram, it kind of looks like it's symmetric around that point, which, you know, you could say flip the slope and add an offset, but that's kind of unethical, so I decided not to do that. So if you go to the next slide, it's just talking a bit about why our result is actually non-physical. So over our test range, steam tables show that latent heat, or latent enthalpy, my apologies, is approximately linear. And then after you do your math and you get your constants, what you should observe is that if you go and look at the steam table values, the regression should produce a value of b that's less than 0. That's the slope. B is the slope of our function. And so as you saw on the previous slide, if you could go back, this is our steam table values right here, and b is negative because our slope is negative. And if you go back, but what we actually got, we got a positive b. That's why it's increasing. So if you go to the next slide, at this point I'm kind of like, all right, did I just do my math wrong? So I checked myself. This can be checked by plugging your data back in, or like reevaluating for a different set of data points. So if you actually use the steam table data instead of the measured data that we got, you can go and run the exact same like analytical solution on it. And if it gives you a value of b that's less than 0, that means that your analytical solution is correct, but something was wrong with your experiment, or you fed the data in wrong. which is what we find because when you calculate it, B is a negative value. Next slide. So some of the sources of error for this, where it could have come from, one thing is that it could have had a pressure offset that won't really change the slope, but it will change the starting point of it. There's also issues about like whether or not it was transient or not, and then also just like issues with the sensors. Next slide, please. But overall, the experiment demonstrates that the Clapeyron equation can be used to estimate the latent enthalpy from saturation pressures and temperatures. However, the method is highly sensitive to experimental errors, just like any experiment, including but not limited to pressure offsets, lack of equilibrium, derivative sensitivity. That's kind of why those first two procedures didn't actually look very good. Boiling temperatures as well. And the final conclusion is that in our data, procedure 3, which is that one that produced a non-physical trend, with the slope of the trend line being greater than 0, which would mean that latent enthalpy rises with temperature, which is non-physical. But overall, Clapeyron is a powerful indirect method for determining latent enthalpy, but reliable results require careful calculation, verification of saturation conditions, and instrumental accuracy. Because that's another thing. We could have been boiling at not saturation pressure or temperature because we didn't have an accurate way to actually like change our pressure. It was changing at a rate prescribed already. We didn't choose that.